Have you ever stopped to listen to the universe, not just with your ears, but with your imagination tuning in to the subtle, rhythmic pulses of light and energy that ripple through the cosmos like notes in a grand, celestial composition? Out there, beyond our atmosphere, the stars aren't just silent pinpricks of light. They're performers in the greatest concert hall of all, each one contributing its own unique voice to a symphony that's been playing for billions of years. This isn't just poetry, it's science. The universe is alive with sound, a mysterious orchestra of vibrations, magnetic fields, and cosmic collisions that create harmonies beyond our wildest dreams. And today, we're stepping into that concert hall to uncover the secrets of a symphony of stars, the mysterious melodies of the Galactic Orchestra. Think about the last time music gave you chills the way a single chord can stir something deep inside you, something primal and wordless. Now imagine that feeling magnified across light years, as entire galaxies hum in frequencies too low for human ears to hear, while neutron stars drum out beats faster than any metronome. These aren't random noises, they're clues. Every whisper of interstellar gas, every shockwave from a supernova carries information about how stars are born, how they live, and how they die. Scientists have learned to translate these cosmic vibrations into sounds we can hear, revealing a universe far more dynamic and musical than we ever imagined. And what they've discovered will reshape how you see and hear the night sky. This journey isn't just about sound, it's about connection. For centuries, humans have looked up at the stars and felt awe, but only recently have we begun to understand that the cosmos isn't just something we observe, it's something we're part of. The same forces that compose these celestial melodies also shaped the atoms in our bodies. The universe isn't just playing music, it's singing our origins. So as we dive into the science behind these cosmic harmonies, from the eerie whistles of solar winds to the deep, resonant hum of black holes, remember, you're not just a spectator. You're part of the symphony, and by the end of this video, you'll never listen to the silence of space the same way again. What if you could press your ear to the fabric of space itself? Beneath the apparent silence, there's a constant thrum of activity, a celestial orchestra where every star, planet, and cosmic event contributes its own distinct note. Take pulsars, for example. These dense, spinning neutron stars act like cosmic lighthouses, beaming radiation across space with such precise timing that scientists compare their pulses to the steady tick of a metronome. Translated into sound, their rapid clicks become rhythmic beats, as if the universe itself is keeping time. Then there are the solar wind streams of charged particles rushing from stars like our sun, creating eerie, whistling tones as they collide with magnetic fields. Even black holes, those enigmatic voids, aren't truly silent. When they merge, they send ripples through space-time called gravitational waves, which scientists can convert into deep, resonant booms like the lowest notes on a cosmic double bass. But how do we hear these sounds? Space, after all, is a near-perfect vacuum where sound waves as we know them can't travel. The secret lies in the vibrations we can detect, light, radio waves, and other electromagnetic signals. Just as a musician plucks a string to create vibrations in the air, celestial events generate waves that ripple through space. Telescopes and satellites act as our cosmic microphones, capturing these signals and converting them into frequencies our ears can process. The result, a symphony of crackling supernova, humming magnetars, and the low, steady drone of interstellar gas, a soundtrack that reveals the hidden dynamism of the cosmos. What makes this orchestra so extraordinary isn't just the individual sounds, but how they interact. Picture a galaxy where newborn stars emit high-pitched chirps of energy, while ancient red giants groan like cellos under their own weight. The solar winds whisper weaves between the crashing cymbals of colliding asteroids, and somewhere in the distance, a black hole's merging crescendo echoes across millions of light years. These aren't random noises, they're the universe's way of telling its story. Every vibration carries data about temperature, density, and motion, helping scientists decode the life cycles of stars and the evolution of galaxies. And just like a symphony, the beauty lies in the harmony, the way these disparate sounds come together to create something far grander than the sum of its parts. This cosmic concert is more than a scientific curiosity. It's a reminder of how interconnected everything truly is. The same forces that compose these celestial melodies also shape the planets, the sun, and even us. When we listen to the stars, we're not just hearing distant phenomena, we're tuning into the very processes that made our existence possible. So the next time you gaze up at the night sky, remember, it's not silent. It's alive with music, a symphony written in the language of physics, waiting for us to press play. Imagine being able to eavesdrop on a star's private conversation with the universe. While we can't hear these cosmic giants directly, science has given us a backstage pass to their vibrations, a secret language of pulses and waves that tells us more than we could ever learn by simply watching their light. This is the world of Asteroseismology, where astronomers act like celestial musicologists, studying the rhythms of stars to uncover their deepest secrets. Just as a guitar string vibrates at different frequencies depending on its tension and length, stars resonate with unique patterns that reveal their internal structure, age, and even their ultimate fate. Take our sun, for example. To the naked eye, it appears as a steady, unchanging ball of light, but sensitive instruments reveal it's actually quivering like a colossal drumhead, with sound waves ricocheting through its plasma interior. These aren't the kind of sound waves we're used to, they're pressure waves created by the turbulent motion of superheated gas. As they travel outward, they cause the star's surface to rhythmically expand and contract, creating subtle changes in brightness that telescopes can detect. By analyzing these oscillations, scientists can peer deep into a star's heart, much like how a doctor uses ultrasound to see inside the human body, the most fascinating part. Each star has its own acoustic fingerprint. Young, massive stars vibrate at higher frequencies, their rapid pulses resembling the upbeat tempo of a pop song. Older stars, like red giants, produce slower, deeper oscillations more like the mournful notes of a double bass. Even more remarkable, these stellar vibrations can tell us about a star's chemical composition. Just as the material of a bell affects its tone, the elements inside a star alter how sound waves travel through it. By studying these acoustic signatures, astronomers have discovered stars with unexpected mixes of hydrogen, helium, and heavier elements, clues that rewrite our understanding of how galaxies evolve. But the real power of asteroseismology lies in its ability to predict stellar futures. The way a star vibrates reveals how much nuclear fuel remains in its core, allowing scientists to estimate how long it has left before it expands into a red giant or collapses into a dense white dwarf. It's as if the stars are singing their own life stories, and we're just beginning to understand the lyrics. When you realize that our sun's quiet hum will one day grow into a red giant's deep groan before fading into a white dwarf's whisper, it adds a profound new dimension to our place in the cosmic timeline. This science doesn't just apply to single stars either. In binary systems where two stars orbit each other, their gravitational dance creates tidal forces that alter their vibrations like duetting singers adjusting their pitch to harmonize. By decoding these complex interactions, researchers have discovered planets orbiting pulsars and even predicted stellar collisions millions of years before they happen. The universe isn't just making noise, it's communicating in a language of vibration that we're finally learning to speak. What makes this especially extraordinary is how recently we've gained this ability. Until the late 20th century, astronomers could only study stars by their light. Now, thanks to space telescopes like Kepler and TESS, which detect minuscule brightness changes with incredible precision, we've entered a new era of cosmic listening. Some researchers compare it to the moment when humans first recorded sound suddenly. We can preserve and study stellar songs that have been echoing through space for eons. And just as early phonograph recordings revealed nuances of human speech no one had noticed before, Asteroseismology is showing us details about stars that visible light alone could never uncover. So the next time you hear a beautiful piece of music, remember the cosmos has been composing far longer than humanity has. Every star is an instrument, every galaxy an ensemble, and we're just beginning to appreciate the symphony. The more we learn to listen, the more we realize that the universe isn't silent at all. It's been singing to us all along. We just needed the right tools to hear it. Pulsars are nature's most astonishing timekeepers, cosmic clocks, so precise they rival our best atomic ones here on Earth. Born from the violent deaths of massive stars in supernova explosions, these spinning neutron stars pack more mass than our Sun into a sphere no bigger than a city. That unimaginable density gives them gravitational pulls strong enough to bend light itself, and magnetic fields trillions of times more powerful than Earth's. But what makes them truly extraordinary is how they sweep beams of radiation across space like interstellar lighthouses, creating pulses so regular you could set your watch by them. Picture a star so dense that a single sugar cube-sized piece of it would weigh as much as a mountain. Now imagine that star spinning hundreds of times per second, whipping its magnetic poles around like a cosmic figure skater pulling in their arms to spin faster. As it rotates, beams of radio waves, X-rays, or gamma rays shoot from its magnetic poles. If those beams happen to sweep across Earth, just like a lighthouse beam momentarily illuminates a ship at sea, we detect them as rapid, rhythmic pulses. Some pulsars flash dozens of times per second, while others take several seconds between pulses, but their timing remains astonishingly consistent. The first pulsar discovered, nicknamed LGM-1 for Little Green Men because its signal seemed so artificial, pulses every 1.337 seconds with a precision that varies by less than 1/1000th of a second per year. What makes these celestial metronomes so reliable? It all comes down to their incredible stability. Unlike regular stars which churn with turbulent plasma, neutron stars are so dense that their crust behaves like a single, rigid crystal. Their spin slows down only gradually as they lose energy, about 1 second every few million years for younger pulsars. That steadiness makes them more accurate than most clocks on Earth. In fact, scientists have proposed using networks of pulsars as a galactic GPS system, their synchronized pulses acting as reference points for spacecraft navigating between stars. But pulsars aren't just precise, they're also cosmic laboratories for testing the laws of physics. When two pulsars orbit each other, their intense gravity causes spacetime to warp, making their pulses arrive at slightly shifting intervals. By tracking these changes, astronomers confirmed Einstein's prediction of gravitational waves decades before we detected them directly. Some pulsars, called millisecond pulsars, spin so fast their surfaces move at a significant fraction of light speed, letting us study matter under conditions impossible to recreate on Earth. Perhaps most poetic is how these dead stars give life to the Galactic Orchestra. Their steady pulses form the underlying rhythm, the bass line of the cosmos against which other stellar sounds play. When a pulsar's beam passes through clouds of interstellar gas, it scatters like light through a prism, creating eerie, echoing harmonies. Some even glitch, suddenly speeding up their spin like a record skipping before settling back into their usual rhythm. These imperfections aren't flaws, they're clues, revealing quakes in the neutron star's crust or mysterious superfluid vortices deep in its core. In the end, pulsars remind us that even in death, stars continue to shape the universe. Their pulses carry messages across millennia, mapping the galaxy's magnetic fields, exposing hidden planets, and whispering secrets about the fundamental nature of space and time. They're not just keeping time, they're telling it, one precise beat at a time. Black holes might appear as cosmic vacuums, swallowing everything, even light, without a trace. But silence, that's an illusion. These gravitational titans are actually some of the loudest performers in the Galactic Orchestra, their voices so deep we've only just learned to hear them. When two black holes spiral toward each other in a final, violent embrace, they don't crash silently. They send ripples through the very fabric of space-time gravitational waves that reverberate like the lowest notes on a piano, so profound they shake the universe itself. Detecting these cosmic bass notes required one of humanity's most audacious experiments, LIGO, the Laser Interferometer Gravitational Wave Observatory. Picture two laser beams traveling down 4-kilometer long tunnels at perfect right angles. When a gravitational wave passes through, it subtly stretches one arm of the detector while squeezing the other, shifting the laser's alignment by less than the width of a proton. That infinitesimal wobble, captured after decades of engineering, delivered the first direct evidence of black holes colliding, a moment that earned scientists the Nobel Prize in Physics. The sound of that event translated into audible frequencies, a quick chirp rising in pitch followed by a deep, resonant thud as the black holes merged into one. But why do these waves sound the way they do? The answer lies in the black holes' dance. As they orbit each other, they emit gravitational waves that carry away energy, causing them to spiral closer. The pitch of the waves rises like a slide whistle, peaking at the moment of collision. The chirp. Then comes the ring down, where the newly formed black hole vibrates like a struck bell, settling into its spherical shape. These vibrations reveal the black hole's mass, spin, and even whether it's perfectly smooth, as Einstein predicted, or textured in ways that could rewrite physics. The most astonishing part, these waves aren't rare. LIGO and its European counterpart, Virgo, now detect them regularly, sometimes weekly. Each event paints a vivid picture. Black holes weighing dozens of suns merging in galaxies billions of light-years away, or neutron stars colliding in explosions that forge gold and platinum. Some waves even hint at intermediate black holes, mysterious objects neither small nor supermassive, whose existence was once debated. Yet the true chorus lies in the lowest frequencies, far deeper than LIGO can hear. Supermassive black holes, millions to billions of times the sun's mass, orbit each other for eons before merging, producing waves with wavelengths so long they could span entire solar systems. To detect these, scientists are turning to pulsars, nature's precision clocks. By monitoring slight timing shifts in pulsar beams as gravitational waves pass through, projects like NanoGrav are listening for a cosmic hum, the combined rumble of every supermassive black hole pair in the universe. Early data suggests this background chorus might already be in earshot, a discovery that could redefine our understanding of how galaxies evolve. What's emerging is a universe thrumming with vibration, where even the darkest objects sing. These waves aren't just curiosities, they're messengers. The chirp of a black hole merger tells us how often these events occur, reshaping estimates of how many black holes lurk unseen. The depth of a ring-down's tone probes the nature of gravity itself, testing whether Einstein's theory holds under extreme conditions, and the background hum. It could reveal whether supermassive black holes merge at all, or stall just shy of collision in a cosmic standoff. So the next time someone calls space silent, you'll know better. Black holes don't just swallow sound, they compose it in frequencies that resonate across spacetime. We're only beginning to tune into this cosmic broadcast, and every new note brings us closer to understanding the universe's deepest secrets. The solar wind is the sun's sigh, a breath of charged particles streaming outward at nearly 1,000,000 miles per hour, carrying its energy far beyond the planets. Though silent to our ears, this relentless gust shapes the very fabric of our solar system, sculpting comet tails, eroding Martian atmospheres, and painting Earth skies with shimmering auroras. But when these particles collide with magnetic fields, they don't just vanish, they sing. Picture Earth's magnetic field as an invisible shield, deflecting most of the solar wind's fury. Where the two forces meet, something extraordinary happens. The charged particles spiral along magnetic field lines, accelerating toward the poles and striking atoms in our atmosphere. These collisions excite oxygen and nitrogen molecules, making them glow, creating the northern and southern lights. But if we could listen to this process, it wouldn't sound like a crash. Instead, scientists have translated the interactions into eerie, whistling tones, like wind howling through celestial canyons. These aren't sound waves in the traditional sense, but fluctuations in electromagnetic energy that, when shifted into our hearing range, reveal a haunting melody. The sun isn't the only star with a voice. Across the galaxy, stellar winds from young, hot stars rage like hurricanes, while older stars exhale slower, dust-laden breezes. When these winds slam into interstellar gas or each other, they generate shock waves that ripple outward, cosmic sound waves traveling through the thin plasma of space. Some of the most dramatic examples come from binary star systems, where two stellar winds collide in a perpetual storm, creating intricate patterns of X-rays and radio emissions that, when sonified, resemble the clash of cymbals in an otherworldly percussion section. But the solar wind's music isn't just for listening, it's a warning system. During solar storms, when the sun unleashes torrents of high-energy particles, the resulting geomagnetic disturbances can disrupt satellites, power grids, and radio signals. By monitoring the sounds of these interactions, the crackle of radio static, the shifts in magnetic oscillations, scientists can predict space weather, giving us time to shield critical technology. What's most humbling is realizing these whispers are ancient. The solar wind has been blowing for over 4 billion years, carrying traces of the sun's composition to the edges of the solar system. When spacecraft like Voyager detected its fading murmur in interstellar space, they weren't just recording data. They were capturing the sun's final farewell, a whisper fading into the cosmic dark. So the next time you see an aurora flickering overhead, remember, you're not just witnessing light, you're seeing the solar wind's song made visible, a fleeting note in a symphony that's been playing since the planets were born. And somewhere, in the magnetic embrace of another star, the same cosmic duet is unfolding, a reminder that the universe never stops singing. Exoplanets aren't just silent specks of rock and gas drifting through space, they're active participants in the cosmic symphony, each one adding its own strange and mesmerizing notes to the Galactic Orchestra. Take the case of hot Jupiters, gas giants that orbit so close to their stars they're literally being roasted alive. These planets don't just endure the heat, they scream under it. Their atmospheres, superheated to thousands of degrees, are ripped away by stellar winds, creating sonic shockwaves that reverberate through space. Scientists call this atmospheric escape, but if we could hear it, it might sound like a relentless, hissing roar, a celestial teakettle left boiling for millions of years. Then there are the singing exoplanets, worlds with conditions so extreme they generate constant, low-frequency hums. Imagine a planet tidally locked to its star, one side eternally scorched while the other freezes in darkness. The temperature difference drives supersonic winds that howl endlessly across the surface, their friction producing vibrations detectable as a deep, droning tone. Or consider lava worlds, where oceans of molten rock churn with such violence that their electromagnetic fluctuations create eerie, pulsing rhythms, like the slow, irregular heartbeat of a planet in perpetual torment. But how do we hear these distant worlds? The answer lies in the subtle ways they interact with their stars. When an exoplanet passes in front of its host star, it doesn't just dim the light, it leaves behind traces of its atmosphere in the starlight, like fingerprints on a window. By analyzing these spectral signatures, astronomers can detect the chemical composition of alien atmospheres, which in turn reveals the potential for sound-generating phenomena. Methane might murmur under pressure while ionized gases crackle with electrical energy. Some researchers have even simulated these sounds, translating atmospheric data into audible frequencies, giving us a chilling preview of what it might be like to stand on the surface of another world. The most astonishing discoveries come from planets that shouldn't exist at all, worlds like WASP 76b, where iron rains from the sky. On the day side, temperatures soar high enough to vaporize metals, while winds carry the iron vapor to the cooler night side, where it condenses and falls as molten droplets. If we could listen, the sound of liquid metal hitting the planet's surface might resemble a slow, metallic drizzle, a soundscape more alien than anything Hollywood could invent. These aren't just curiosities, they're clues. The music of exoplanets tells us about their weather, their geology, even their potential to harbor life. A planet with a rhythmic, stable hum might have a thick atmosphere capable of regulating temperature, while one with chaotic, screeching harmonics could be a turbulent hellscape. As we discover more of these distant performers, we're not just expanding our catalog of planets, we're learning to listen to the stories they've been telling all along. And somewhere in the harmonies of an undiscovered world, there might be a note we've never heard before, one that changes everything. Between the stars, where space seems emptiest, floats an invisible choir, vast clouds of gas and dust so thin that a handful of their atoms would fill a cathedral. Yet these interstellar nurseries, some spanning hundreds of light years, are anything but silent. Their molecules vibrate with a faint, ethereal music, a chorus of chemical bonds stretching and twisting in the cold dark. When scientists translate these vibrations into sound, the result is haunting. Ghostly harmonies that shift from low drones to crystalline high notes, like wind humming through cosmic chimes. What makes these clouds sing? It all comes down to chemistry. Every molecule, whether simple hydrogen or complex organic compounds, vibrates at specific frequencies as its atoms wobble and spin. Carbon monoxide molecules, for example, emit a tone around 440 gigahertz, far beyond human hearing. But when radio telescopes like ALMA in Chile detect these signals, we can scale them down to audible frequencies, revealing a soundscape as intricate as a symphony. Some clouds thrum with deep bass notes from swirling hydrogen, while others crackle with the high-frequency chirps of complex molecules like cyanide or formaldehyde. Together, they form a celestial hymnbook, each note revealing the cloud's composition, temperature, and even its motion through space. But these aren't just random noises, they're birth cries. Inside these clouds, gravity pulls gas into dense knots that eventually ignite as stars. The vibrations act like sonar, letting astronomers map the hidden structure of stellar nurseries. A sudden shift from orderly harmonies to chaotic dissonance might signal the moment a cloud fragment collapses to form a protostar. In the Orion Nebula, scientists have even detected sound waves moving through the gas, not true sound, but pressure ripples that trigger new star formation like a cosmic domino effect. The most mesmerizing clouds are the dark, cold ones where temperatures hover just above absolute zero. Here, molecules move sluggishly, their vibrations stretched into deep, resonant tones. Some of these clouds are so rich in organic compounds that their spectra resemble the chemical building blocks of life. When sonified, their harmonies take on an almost melodic quality, as if the universe itself is composing a lullaby for newborn planets. What's truly astonishing is how much these sounds tell us. By analyzing the chords of a gas cloud, astronomers can predict how many stars it will birth, how massive they'll be, and even whether they'll form with planetary systems. A cloud singing in rich, complex harmonies likely has the diversity of elements needed for rocky worlds, while one emitting only simple tones might only muster gas giants. It's as if the universe leaves voicemails about its future, and we're finally learning to listen. So the next time you look at the dark patches in the Milky Way, remember, they're not voids. They're stages where gravity conducts an orchestra of molecules, tuning up for the next act of star formation. And in their vibrations, we hear echoes of our own solar system's lullaby, played 4.5 billion years ago. Gravitational waves are the universe's deepest, most resonant notes, a bassline so low it vibrates the fabric of reality itself. Picture dropping a pebble into a still pond, watching the ripples spread outward. Now imagine that pebble is a black hole with 30 times the mass of our Sun, and the pond is space-time. That's the essence of a gravitational wave. An invisible distortion racing across the cosmos at the speed of light, stretching and squeezing everything in its path by distances smaller than an atom. For decades, these waves existed only in Einstein's equations, a ghostly prediction of general relativity. Then, in 2015, humanity finally heard them, a faint chirp lasting less than a second, born from two black holes colliding 1.3 billion light-years away. What makes this discovery so revolutionary isn't just the confirmation of Einstein's genius. It's the realization that space isn't a static stage where cosmic events unfold. It's a dynamic, rippling medium that carries the echoes of the universe's most violent symphonies. Every massive acceleration, black holes merging, neutron stars spinning into each other, even the Big Bang itself, sends gravitational waves pulsing outward like the beat of a cosmic drum. The frequencies are far too low for our ears to hear naturally, but when scientists shift them into our audible range, the result is a haunting, minimalist composition, a sudden upward sweep followed by a deep, reverberating thud. These waves aren't just sounds, they're messengers. Unlike light, which can be blocked by dust or distorted by gravity, gravitational waves pass through everything unimpeded, carrying pristine information about their origins. A single detection can reveal the masses of colliding black holes, their spins, even the direction they're rotating. When two neutron stars merged in 2017, their gravitational waves arrived alongside a gamma-ray burst and a flash of light rich with heavy metals like gold and platinum, proof that these cosmic crashes are forges of the universe's rarest elements. But the real magic lies in the collective hum. Just as individual instruments blend into an orchestra's harmony, countless gravitational wave events across the universe create a background noise, a constant, ultra-low frequency vibration that permeates all of space. Detecting this chorus requires thinking even bigger than LIGO 4-kilometer arms. Enter pulsar timing arrays, networks of dead stars whose lighthouse-like beams serve as galactic metronomes. As gravitational waves pass between Earth and these pulsars, they subtly alter the timing of the pulses, creating patterns that reveal the wave's presence. Early data suggests we're on the verge of hearing this cosmic murmur, the summed rumble of every supermassive black hole duo in the universe, a sound that could help us map the unseen structure of the cosmos. Perhaps most astonishing is what these waves say about spacetime itself. When black holes merge, their gravitational waves carry a signature called ring-down, a fading series of vibrations as the new, larger black hole settles into its spherical shape. The tone and decay of this ring-down are like a fingerprint, revealing whether spacetime behaves exactly as Einstein predicted, or if there are hidden layers we've yet to uncover. Some theories suggest that at extremely small scales, spacetime might be foamy, a quantum froth that could slightly distort gravitational waves. Others propose extra dimensions that would add new harmonics to the wave's structure. Every new detection is like tuning into a cosmic radio station, each song testing the laws of physics in ways light never could. So the next time you hear a deep bass note in music, think of gravitational waves, the universe's own rhythm section. They've been playing for billions of years, long before life emerged to hear them. And now, thanks to a century of scientific ingenuity, we've joined the audience, listening as black holes dance, neutron stars collide, and the very fabric of reality sings. 2,500 years ago, Pythagoras stood under the night sky and heard music no one else could, a celestial harmony woven into the very fabric of existence. Legend says he noticed blacksmiths' hammers striking anvils produced different pitches based on their weights, sparking his revelation. The universe might follow similar mathematical ratios. He envisioned the planets orbiting in perfect intervals, their movements creating a cosmic scale, the harmony of the spheres. Though silent to human ears, Pythagoras believed this music echoed through the cosmos, a divine symphony audible only to the soul. Centuries later, Johannes Kepler took up the torch. Obsessed with finding order in the heavens, he spent years analyzing planetary orbits, convinced they traced geometric patterns that corresponded to musical notes. In his groundbreaking work Harmonies Mundi, he assigned each planet a pitch based on its speed. Saturn a deep G, Jupiter an E, Mars a tenor D, all the way to Mercury's high F. To Kepler, the solar system wasn't just moving, it was singing, its harmonies occasionally slipping into dissonance during rare planetary alignments. What's astonishing isn't that he was wrong about the mechanics, but how eerily close he was to a truth we're only now confirming. Fast forward to today, and modern astrophysics reveals the universe does vibrate, just not in the way Pythagoras or Kepler imagined, those harmonic ratios they sought. They're encoded in the orbital resonances of exoplanets, where neighboring worlds tug on each other until their orbits synchronize like perfectly tuned strings. The music Kepler yearned to hear, it's real, but not as melodies, rather as the oscillations of stars, the electromagnetic hum of magnetospheres, and the gravitational waves rippling from colliding black holes. Even Earth's magnetic field, when struck by solar wind, emits ultra-low frequency chorus waves that sound like birdsong when sped up. The bridge between ancient wonder and modern science lies in mathematics. Pythagoras ratios govern the vibrational modes of stars studied through asteroseismology. Kepler's geometric harmonies mirror the fractal patterns of galaxy clusters. What once seemed mystical now fits neatly into equations describing plasma vibrations, orbital dynamics, and quantum fluctuations in the vacuum of space. The universe isn't playing literal notes, but its rhythms, whether in the pulse of a quasar or the spin of a neutron star, follow mathematical cadences that feel almost musical. Perhaps the most poetic validation comes from Saturn. When the Cassini spacecraft analyzed the planet's rings, it discovered spiral density waves ripples created by the gravitational pull of its moons that behave exactly like sound waves. Translated into audible frequencies, they produce eerie, ethereal tones. Even Saturn's auroras emit radio waves that, when processed, resemble the crackle of distant thunderstorms. It's as if the cosmos took Kepler's dream and said, "Wait, you haven't heard the half of it." This enduring fascination speaks to something deeper than science. From ancient philosophers to modern astronomers, humanity keeps returning to the idea of cosmic music because it marries logic with wonder. The universe does sing, not in melodies we can hum, but in vibrations that reveal its hidden structure. Every time we convert data into sound, whether the rumble of a black hole or the whistle of solar wind, we're not just analyzing, we're listening, just as Pythagoras did to the oldest song there is. And with each discovery, the symphony grows richer. NASA sonification projects are like cosmic translators, turning the silent beauty of space into something we can experience not just with our eyes, but with our ears. Take the pillars of creation, for example, those towering columns of gas and dust in the Eagle Nebula immortalized by Hubble. Invisible light, they're breathtaking. But when NASA team sonified the data, they assigned different tones to elements like oxygen, hydrogen, and sulfur based on their wavelengths. The result: a shimmering, almost ghostly melody that rises from the base of the pillars to their peaks, as if the nebula itself is singing its own creation story. This isn't just artistic interpretation, it's science with purpose. By mapping brightness and position to pitch and volume, sonification reveals patterns our eyes might miss. In the Perseus galaxy cluster, Chandra X-ray Observatory detected pressure waves rippling through superheated gas around a central black hole. Translated into sound, those waves become an eerie, resonant hum 60 octaves below middle C, a note so deep it's more felt than heard. It's the lowest tone in the known universe, a bass line that's been playing for 2.5 billion years. Some of the most striking sonifications come from composite data. The Crab Nebula, a supernova remnant, combines X-rays from Chandra, visible light from Hubble, and infrared from Spitzer. Each telescope's data becomes an instrument, X-rays as sharp, metallic percussion, visible light as sustained strings, and infrared as a warm, synth-like drone. Layered together, they create a haunting soundscape that mirrors the nebula's chaotic beauty. But these projects aren't just about awe, they're about access. For visually impaired astronomers like Dr. Nick Bond, sonification opens doors. By training his ear to recognize the sound of different stellar phenomena, he can analyze data independently. A spiral galaxy's arms might spiral upward in pitch, while a supernova's shockwave rings out like a cymbal crash. This isn't just accommodation, it's a new way of doing science, proving the universe communicates in more ways than we imagined. What's truly revolutionary is how sonification exposes hidden relationships. In the Whirlpool galaxy, assigning pitch to distance from the core reveals an asymmetry in its spiral arms. One side's notes rise faster, hinting at gravitational disturbances from a neighboring galaxy. Similarly, the heartbeat of a pulsar's gamma-ray emissions when sped up matches the rhythm of human music almost uncannily, as if the cosmos has an innate sense of tempo. NASA team even sonifies entire cosmic events. The 2017 neutron star merger, detected through gravitational waves and light, became a crescendo of chimes and deep thrums, a soundtrack to the birth of gold and platinum. These projects remind us that data isn't just numbers, it's a story waiting to be heard, and as we listen, we're not just observers, we're part of the audience in the grandest concert hall of all. Deep in the cosmic background, beneath the crash of supernova and the whisper of solar winds, lies a mystery that's been quietly puzzling astronomers for years, a persistent, low-frequency hum echoing across the universe. Unlike the sharp chirps of colliding black holes or the rhythmic pulses of neutron stars, this sound is diffuse, all-encompassing, like the static of an old radio tuned to the space between stations. First detected by radio telescopes as a faint, omnipresent buzz, this hum defies easy explanation. It's not tied to any single galaxy or event. Instead, it seems to permeate the fabric of space itself, a sonic backdrop to the cosmos. One leading theory suggests we're hearing the collective voice of countless stars, their stellar winds, supernova, and magnetar flares blending into a cosmic white noise. Imagine standing in a crowded stadium where every cheer, clap, and shout merges into a single roar. Now scale that up to galactic proportions, with trillions of stars contributing their vibrations across billions of years. The hum could be the universe's way of tallying its most common, everyday phenomena, the routine cacophony of star birth and death we've been too focused on individual events to notice. But there's a twist. The hum's intensity doesn't quite match what stellar activity alone should produce. That discrepancy has led some scientists to propose a far more exotic origin, dark matter. This invisible substance, which outweighs ordinary matter 5 to 1, barely interacts with light or sound. Yet if dark matter particles occasionally collide or decay, they might generate faint waves in the plasma between galaxies, creating a subtle vibration our telescopes pick up as background noise. It's a tantalizing idea, the hum as the first audible clue to the universe's most elusive ingredient. Then there's the black hole angle. Supermassive black holes at the centers of galaxies are thought to merge often, their gravitational waves rippling outward. While individual collisions produce distinct chirps, the combined echoes of countless mergers over cosmic time could blend into a steady drone, like raindrops in a storm merging into a single patter. Recent simulations suggest this black hole chorus might match the hum's frequency, offering a way to estimate how often these giants collide. The challenge lies in untangling the signal from the noise. Radio astronomers use sophisticated algorithms to filter out interference from Earth's atmosphere, satellite transmissions, and even the Milky Way's own radio buzz. What remains is a sound so faint it's like trying to hear a whisper in a hurricane. Yet as telescopes grow more sensitive, like the upcoming Square Kilometre Array with its thousands of linked antennas, we're inching closer to isolating the hum's true source. What's most thrilling is the hum's potential to rewrite cosmic history. Its uniformity suggests it's been playing since the universe was young, a fossilized echo of an era when galaxies were first clumping together. If dark matter is involved, the hum could reveal how this mysterious substance shaped the universe's large-scale structure. Or if it's stellar in origin, it might force us to reconsider just how much energy stars pour into space over their lifetimes. For now, the hum remains an enigma, a reminder that even in an age of gravitational wave detectors and space telescopes, the cosmos still hums its secrets just beyond our understanding. But with every new observation, we're tuning our instruments finer, learning to listen more closely. And somewhere in that static, the universe might be telling us a story we've only just begun to hear. A supernova doesn't just mark the death of a star. It's a cosmic crescendo, a final, deafening shout that rips through the silence of space with the energy of 100 billion suns. When a massive star exhausts its nuclear fuel, Its core collapses in less than a second, rebounding with such force that it tears the star apart in a cataclysmic explosion. The shock waves from this detonation race outward at millions of miles per hour, compressing and heating the surrounding gas until it glows brighter than an entire galaxy. But what we see as light is only part of the story. These shock waves also generate pressure waves, cosmic sound waves, that propagate through interstellar clouds like thunder after lightning, leaving behind ripples detectable for millennia. Scientists first captured these echoes in the remnants of Cassiopeia A, a supernova whose light reached Earth around 300 years ago. By analyzing the ripples in its expanding debris field, researchers realized the explosion hadn't been symmetrical. Instead, it had unleashed a chaotic blast of sound waves, like a drummer striking a cymbal off-center. When translated into audible frequencies, these waves reveal a sharp, metallic crash followed by a fading reverberation, a sonic fingerprint of the star's violent demise. Other supernovae leave different signatures. The famous Crab Nebula's waves resonate at a deeper pitch, more gong-like, hinting at the slower collapse of its progenitor star. These variations aren't just celestial curiosities. They're clues about how stars die, how heavy elements scatter into space, and even how future shockwaves might trigger the birth of new stars. But the loudest notes come from rare hypernova, stellar explosions 100 times more energetic than typical supernova. Thought to accompany the birth of black holes or magnetars, these events generate gravitational waves so powerful they momentarily stretch spacetime itself. The sound of a hypernova, if we could hear it directly, might resemble a deep, rolling boom, a cosmic drumroll announcing the arrival of something extraordinary. What's most astonishing is how far these sounds travel. The shock waves from supernova can sweep through entire galaxies, plowing into interstellar gas and triggering chain reactions of star formation. In the Orion Nebula, astronomers have found evidence of ancient supernova echoes still pushing gas into denser clumps, like sonic sculptors shaping the next generation of stars. Even our solar system might owe its existence to such an explosion. The slight excess of radioactive isotopes in meteorites suggests a nearby supernova's shockwave could have jump-started the collapse of the molecular cloud that became our sun and planets. Yet for all their fury, supernova also compose the universe's most poignant harmonies. In their ashes, they forge the iron in our blood, the calcium in our bones, and the oxygen we breathe. Their explosions are both endings and beginnings, cosmic symbols crashing to mark the close of one stellar symphony, while quietly tuning the instruments for the next. Dark matter is the universe's most elusive conductor, an invisible hand guiding the movements of galaxies and stars without ever making a sound. Though it neither emits nor absorbs light, its gravitational pull sculpts the cosmos on a scale so vast it determines where and how celestial objects dance. Picture a grand orchestra where the musicians are stars, planets, and gas clouds, all following sheet music written in the language of gravity. Dark matter is the silent maestro, unseen but essential, ensuring every note lands in perfect harmony. Take galaxy rotation, for example. In the 1970s, astronomer Vera Rubin noticed something peculiar. The outer stars of spiral galaxies were moving just as fast as those near the center. According to Newton's laws, these distant stars should have been lagging behind, like children at the end of a spinning merry-go-round. The only explanation: an enormous halo of invisible matter, dark matter wrapping around each galaxy, its gravity holding the outer stars in place. Without it, galaxies would fly apart, their stellar symphonies reduced to discordant chaos. But dark matter's influence goes far beyond anchoring individual galaxies. It weaves the cosmic web, a sprawling network of filaments and voids that stretches across the universe. Where these filaments intersect, galaxies cluster like pearls on a string, drawn together by dark matter's gravitational embrace. These clusters aren't just static gatherings, they're dynamic stages where galaxies collide, merge, and trigger bursts of star formation. The resulting shockwaves ripple through intergalactic gas, creating pressure waves that, if we could hear them, might sound like the distant rumble of timpani. Even stranger are the anomalies dark matter leaves in its wake. When light from distant galaxies passes near massive galaxy clusters, it bends, a phenomenon called gravitational lensing. But often, the distortion is stronger than the visible mass can account for, revealing hidden pockets of dark matter warping spacetime like an unseen hand pressing down on a drumhead. Some of these lenses even produce multiple images of the same galaxy, a cosmic echo effect that lets astronomers map dark matter's distribution with astonishing precision. The most tantalizing clue to dark matter's role in the cosmic symphony comes from the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light reveal how matter clumped together in the early universe. Without dark matter's gravitational scaffolding, ordinary matter would have spread too thinly, and galaxies might never have formed at all. In other words, the universe's first notes, the primordial vibrations that eventually grew into stars and planets, were orchestrated by something we still can't see or hear. Yet for all its power, dark matter remains frustratingly silent. Unlike black holes or neutron stars, it doesn't collide, merge, or vibrate in ways that produce detectable waves. Its music is written in the spaces between the slow, stately dance of galaxies drifting toward one another, the invisible threads tying the cosmos together. Some theories suggest dark matter particles might occasionally interact, emitting faint signals we've yet to detect. Others propose it could be part of a hidden sector of physics, with its own rules and vibrations entirely separate from ours. What's certain is this: the universe's grand composition wouldn't exist without dark matter's unseen influence. From the birth of galaxies to the fate of the cosmos itself, it's the silent force behind every movement, every collision, every note in the celestial score. And as we listen ever closer to the cosmos, we're not just hearing the music of the stars, we're beginning to sense the presence of the conductor we've never seen. Among the most extreme performers in the Galactic Orchestra, Magnetars stand out as cosmic violins, neutron stars that don't just hum or pulse, but shriek with the fury of 1,000 suns. Imagine a stellar remnant so dense that a teaspoon of its material would weigh 1 billion tons, spinning faster than a kitchen blender, and wrapped in a magnetic field strong enough to erase your credit card from halfway across the solar system. When these fields twist and snap under unimaginable strain, they unleash starquakes, violent rearrangements of the star's crust that send shockwaves rippling through space. The energy released isn't just light or heat, it's a scream across the electromagnetic spectrum, a vibration so intense it can briefly outshine every other source in the galaxy. If we could hear these outbursts, they'd slice through the cosmic noise like a bow drawn sharply across violin strings, piercing, urgent, and hauntingly beautiful. What makes Magnetars so extraordinary is how they transform destruction into music. Their magnetic fields, a quadrillion times stronger than Earth's, act like cosmic rubber bands stretched to the breaking point. When they finally recoil, the energy released cracks the star's solid iron crust, sending tremors through its interior. These quakes generate gamma-ray flares and X-ray pulses that ripple outward in precise frequencies, some as regular as the notes on a musical scale. In 2004, a magnetar 50,000 light-years away unleashed a flare so powerful it compressed Earth's upper atmosphere. all from an object no wider than Manhattan. Converted into sound, that event would resemble a sudden, ear-splitting glissando, a rapid slide up the cosmic scale that fades into an eerie whisper. Yet Magnetars don't just play solo. Their vibrations interact with the surrounding universe in surprising ways. Some emit steady X-ray songs as they rotate, their beams sweeping past Earth like a lighthouse with a musical siren. Others, like the Magnetar in the constellation Sagittarius, produce sudden, unpredictable bursts, staccato notes that punctuate the galactic symphony like exclamation points. These outbursts aren't random. They follow patterns that hint at the physics of ultra-dense matter, offering clues about how particles behave under pressures so extreme that atoms collapse into bizarre quantum soups. The rarest Magnetar performances are their anti-glitches, moments when the star suddenly slows its spin, the opposite of what neutron stars usually do. It's as if a violinist briefly dug their bow backward against the strings, creating a disorienting hiccup in the rhythm. Astronomers suspect these events occur when the star's crust fractures so severely that part of it sinks inward, dragging the magnetic field lines with it like an anchor. The resulting vibrations, translated into sound, might mimic the dissonant twang of a snapped string suddenly retuned. But Magnetars aren't just celestial oddities, they're timekeepers. Their precise pulses help astronomers map the distribution of matter in space, as intervening gas and dust subtly delay their signals. Some researchers even propose using Magnetar flares as cosmic sirens to measure the universe's expansion, their light carrying echoes of the space it's traveled through. And when two Magnetars eventually collide, their merging magnetic fields could generate gravitational waves unlike any we've detected before, a crescendo of space-time ripples that might sound like a violin's final, shuddering note. In the end, Magnetars remind us that the universe's music isn't always harmonious. Sometimes it's the screech of bending metal, the snap of breaking chains, the cry of a star tearing itself apart to be heard across the void. These cosmic violins don't just add texture to the Galactic Orchestra, they redefine what music can be. Before stars or galaxies existed, even before atoms had fully formed, the infant universe was a seething ocean of plasma so dense that light couldn't travel more than a fraction of an inch before scattering. Yet this chaotic soup wasn't silent. Packed with particles and crackling with energy, it thrummed with pressure waves, sound waves that surged through the cosmos like ripples across a pond. These weren't ordinary sound waves, though. With no air to carry them, they propagated through the plasma itself, compressing and rarefying it in rhythmic pulses that shaped the universe's very structure. Today, we can still detect their echoes imprinted on the oldest light in existence, the cosmic microwave background, a faint glow released when the universe cooled enough to become transparent. What makes these primordial vibrations so extraordinary is how they reveal the universe's first moments. Picture dropping a stone into water, the ripples spread outward, their size and speed telling you about the stone's weight and the water's depth. Similarly, the sound waves from the early universe carry information about its density, temperature, and composition. By analyzing the spacing between these wave patterns in the cosmic microwave background, scientists discovered that the early cosmos was a near-perfect fluid, vibrating at frequencies so low they'd be 57 octaves below middle C if translated into audible sound. That's deeper than the lowest note on a piano, deeper than anything human ears could perceive. The origin of these sound waves traces back to quantum fluctuations, tiny, random variations in density that emerged in the first fraction of a second after the Big Bang. As the universe expanded, gravity amplified these fluctuations, pulling matter into denser regions while leaving voids between them. The resulting push and pull pull created oscillations, with matter rushing inward under gravity's pull, then rebounding outward as radiation pressure pushed back. Each oscillation lasted tens of thousands of years, leaving behind a series of frozen peaks and troughs in the cosmic microwave background like grooves on a vinyl record preserving the universe's first song. Remarkably, the dominant note in this cosmic chord was a single, resonant frequency determined by the speed of sound in the early plasma. As the universe cooled, the waves froze at a characteristic distance about 500,000 light-years that now serves as a universal measuring stick. When telescopes like Planck mapped the cosmic microwave background, they found this distance imprinted as a preferred scale in the distribution of galaxies. In other words, the sound waves from the infant universe didn't just fade away, they set the blueprint for everything that followed, determining where galaxies would eventually cluster and how they'd arrange themselves across the cosmos. Some of the most profound insights come from the harmonics, the overtones riding atop that fundamental frequency. Just as a plucked guitar string vibrates at multiple frequencies simultaneously, the early universe's oscillations created a series of peaks in the cosmic microwave background's power spectrum. The relative heights of these peaks reveal the universe's composition. How much is ordinary matter, how much is dark matter, and how much is dark energy? They even hint at the number of neutrino species, ghostly particles so elusive they barely interact with anything at all. Perhaps the most astonishing realization is that we're not just observers of this ancient music, we're part of it. The same sound waves that sculpted galaxies also seeded the slight variations in density that allowed our solar system to form. The atoms in our bodies were once part of those primordial vibrations, their distribution shaped by oscillations that began before time had meaning. When scientists listen to the cosmic microwave background, they're not just studying the past, they're hearing the first notes of a symphony that's still playing, with every star, planet, and galaxy dancing to a rhythm set in the universe's first moments. Quasars are the rock stars of the cosmos, supermassive black holes turned up to 11, devouring matter with such ferocity that they outshine entire galaxies. These screaming giants sit at the heart of distant star systems, their insatiable appetites generating jets of radiation so intense they can be seen clear across the universe. But what makes them truly extraordinary isn't just their light. It's the chaotic, deafening roar they add to the galactic symphony. At the core of every quasar lies a black hole millions to billions of times more massive than our Sun, surrounded by a swirling disk of superheated gas and dust. As material spirals inward, friction heats it to temperatures so extreme it glows brighter than a trillion stars. But the real spectacle happens at the poles, where magnetic fields funnel some of that energy into narrow jets traveling near light speed. These jets slam into surrounding gas clouds, creating shock waves that ripple through space, a cosmic feedback loop of violence and vibration. When scientists convert these interactions into sound, the result is a frenetic, high-pitched screech, like feedback from an overdriven amplifier. What makes quasars unique in the cosmic orchestra is their sheer volume. While pulsars keep a steady beat and magnetars unleash sporadic screams, quasars produce a relentless, broadband noise spanning the entire electromagnetic spectrum. Their jets emit everything from radio waves to gamma rays, each frequency carrying its own sonic signature when translated into audible sound. The radio emissions might resemble static hiss, while X-rays crackle like bacon in a frying pan. Combined, they create a dissonant cacophony that drowns out subtler cosmic melodies for light years around. Yet these screaming giants aren't just making noise, they're shaping their galaxies. The energy blasting from quasars can heat interstellar gas so thoroughly it stifles star formation, effectively putting a galaxy's growth on hold. In some cases, their jets carve vast bubbles in surrounding gas clouds, leaving behind hollowed-out voids that resonate like cosmic drumheads. Astronomers have even detected quasar echoes, delayed reverberations of light bouncing off dust clouds, a phenomenon akin to hearing your voice bounce back in a canyon. The most fascinating quasars are those caught in the act of merging. When two galaxies collide, their central black holes spiral toward each other, feeding frenziedly and producing dual jets that twist into chaotic helices. These interactions generate gravitational waves, deep, thrumming notes that hum beneath the electromagnetic screech. Future telescopes hope to detect this harmony of gravity and light, revealing how the universe's loudest objects orchestrate their most destructive duets. Quasars also serve as cosmic time capsules. Because light takes billions of years to reach us from the most distant ones, we're effectively hearing the universe's early adolescence, a time when black holes and galaxies were growing at breakneck speed. Their screams carry clues about how structures formed in the ancient cosmos, and why some black holes became monstrous while others stayed relatively quiet. In the end, quasars remind us that the universe isn't just a collection of pretty lights. It's a dynamic, often violent arena where gravity and radiation compose a soundtrack as complex as it is cacophonous. And while we can't hear their screams directly, the data paints a vivid picture, one where even the darkest objects refuse to stay silent. Binary stars don't just share the same stage, they perform an intricate celestial waltz, their gravitational embrace choreographing a dance that resonates across the cosmos. Picture two stars locked in orbit, their mutual pull stretching and compressing each other like cosmic accordions. As they swing closer together, tidal forces distort their shapes, triggering vibrations that ripple through their interiors. These oscillations aren't random, they're precise, rhythmic pulses that mirror the mathematical harmonies of a musical duet. When astronomers translate these vibrations into sound, some binary systems produce tones so perfectly synchronized they could be mistaken for a composed piece of music. Take the case of Kepler 4718661, a binary pair separated by just a few million miles. As the stars orbit every 1.5 days, their mutual gravity tugs at their surfaces, creating pressure waves that propagate through their cores. These waves amplify certain frequencies while canceling out others, a phenomenon known as resonant coupling. The result, a harmonic series of pulsations where one star's vibrations lock into step with the others, like two singers harmonizing in perfect fifths. Scientists call this tidally induced oscillation, but in essence, it's the universe's version of a call and response ballad. What makes these stellar duets so valuable to astronomers isn't just their beauty, it's the secrets they reveal. The precise timing of a binary system's pulses acts as a cosmic tuning fork, allowing researchers to measure the star's masses, sizes, and even their internal compositions with extraordinary accuracy. For example, if one star's vibrations arrive slightly out of phase with its partners, it could hint at asymmetrical internal structures or hidden magnetic fields warping their interactions. In extreme cases, these distortions expose the presence of unseen planets or the faint gravitational whispers of dark matter halos enveloping the system. Some binary stars take this harmony to even greater extremes. In heartbeat stars, the gravitational pull between the pair is so strong that their orbits stretch them into egg-shaped distortions at their closest approach, then let them relax into spheres as they swing apart. This rhythmic deformation causes their brightness to flicker in a pattern that, when sonified, mimics the steady thump of a heartbeat. The most famous example, KOI 54, pulses every 41 days with such regularity that its light curve resembles an electrocardiogram, a celestial EKG printed across the fabric of space. But not all stellar duets are so serene. In cataclysmic variable systems, a white dwarf siphons material from its companion star, funneling it into a swirling accretion disk that occasionally erupts in thermonuclear explosions. These violent outbursts send shockwaves through the surrounding gas, creating erratic, staccato bursts of X-rays that, when converted into sound, resemble the chaotic crash of cymbals. Yet even in these turbulent relationships, there's an underlying order. The intervals between eruptions often follow predictable patterns, offering clues about the rate of mass transfer and the white dwarf's eventual fate as it inches toward a possible supernova. The most profound insight binary stars provide is how they shape their own destinies. Over billions of years, their gravitational tango can lead to spectacular finales. Some pairs spiral closer until they merge in a fiery collision, creating a single, more massive star. Others, like the double pulsar system PSR J0737-3039, gradually widen their orbits as they lose energy to gravitational waves, their rhythmic pulses slowing like a record player winding down. Each outcome leaves behind a unique acoustic fingerprint, a fleeting echo of the forces that govern their lives. In the end, binary stars remind us that the universe's music isn't just about solo performers. It's a collaborative effort where gravity composes the score and stars bring it to life, their intertwined rhythms revealing the hidden laws of physics in every note. And as we listen, we're not just hearing their stories, we're discovering how even the simplest cosmic relationships can create harmonies more complex than anything we could compose ourselves. Cosmic strings may be the most elusive instruments in the universe's orchestra, threads of pure energy thinner than an atom but stretching across billions of light years, remnants of the cosmos's fiery infancy. According to theoretical physics, these bizarre defects in space-time formed during the universe's first moments, when the fundamental forces hadn't yet settled into their current states. Like cracks freezing into ice, these imperfections could have been locked into the fabric of reality as the universe cooled, leaving behind ultra-dense, vibrating filaments under unimaginable tension. If they exist, their oscillations wouldn't just ripple through space, they'd sing, emitting gravitational waves at frequencies so high they'd dwarf even the sharpest notes of a pulsar. The sound of a cosmic string would be unlike anything else in nature. Picture plucking a guitar string stretched between galaxies, except instead of vibrating a few hundred times per second, it shimmers at millions or even billions of cycles per second, a pitch so extreme it would register as a screech far beyond human hearing. These vibrations wouldn't travel through air or plasma, but through space-time itself, warping the distances between stars and planets as they pass. When two cosmic strings cross or snap, the event would unleash a burst of gravitational waves, a staccato ping reverberating across the cosmos. Some theories suggest these snaps could even seed the formation of new cosmic strings, like a never-ending cascade of falling dominoes, each ringing their own microscopic bell. What makes cosmic strings especially fascinating is how they'd interact with the rest of the universe. Their immense gravity, so strong that a single inch of string might weigh as much as a mountain, would bend light around them, creating double images of distant galaxies like a flaw in a cosmic lens. If a string passed through Earth, it wouldn't slice the planet in half as sci-fi might suggest, but it would warp time itself, causing clocks on one side of the string to tick fractionally faster than those on the other. And just as a violin string's harmonics reveal its material and tension, the vibrations of cosmic strings could expose secrets about the universe's earliest moments, back when energy and matter were indistinguishable. The hunt for these phantom strings is already underway. Astronomers scour the cosmos for anomalous patterns in the cosmic microwave background, straight-line discontinuities that might betray a string's passage. Others analyze pulsar timing arrays for sudden, unexplained shifts that could signal a string's gravitational wake. While no definitive detection has been made, some researchers speculate that certain repeating fast radio bursts, mysterious, high-energy signals from deep space, might align along invisible cosmic strings like beads on a wire. Even if these strings remain hypothetical, their potential existence reshapes our understanding of cosmic music. The universe's symphony might include instruments we can't yet see, playing notes we're only beginning to imagine. In the grand composition of the cosmos, cosmic strings would be the theremin section, ethereal, enigmatic, and operating on principles that defy everyday intuition. Their music wouldn't just fill the gaps between stars, it would weave the very stage on which the Galactic Orchestra performs. And if we ever do detect their vibrations, it won't just confirm a theory, it'll unveil a new movement in the universe's oldest song, one written in the language of space-time itself. Here's a paradox: the universe is alive with vibrations, yet space itself is utterly silent. If you were floating in the void between stars without a spacesuit, the only thing you'd hear is the rush of blood in your own ears. Not a whisper of solar wind, not a murmur from distant stars. The reason comes down to one simple fact: sound, as we experience it, needs a medium to travel through, whether that's air, water, or the ground. In the near-perfect vacuum of space, there's nothing for those vibrations to push against, no molecules to compress and rarefy in waves. It's like having the most powerful speaker in existence blasting music into an empty room with no walls to echo off. But that doesn't mean space is truly mute. What we can't hear with our ears, we've learned to detect with technology. Take the sun, for example. Its surface churns with plasma, generating pressure waves that ripple outward like the booming notes of a cosmic bass drum. These waves travel through the sun's dense interior, but the moment they reach the vacuum of space, they vanish not as sound, but as vibrations in magnetic fields and charged particles. Scientists use instruments like the Solar Dynamics Observatory to capture these oscillations, translating them into frequencies our ears can process. The result, a deep, resonant hum, as if the sun is singing behind an impenetrable glass wall. Then there's the electromagnetic chorus: radio waves, X-rays, and gamma rays emitted by everything from pulsars to colliding galaxies. These aren't sound waves, but when researchers shift their frequencies down into the audible range, the cosmos suddenly comes alive with crackles, whistles, and rhythmic pulses. The Voyager probes, for instance, recorded plasma vibrations in the thin gas between stars, revealing a haunting whisper of interstellar space. Even the cosmic microwave background, the afterglow of the Big Bang, has been sonified into a low, hissing drone, like the static of an untuned radio carrying echoes of creation itself. The most dramatic transformation comes from gravitational waves. When black holes collide, they don't produce sound in the traditional sense, but their ripples in space-time can be converted into audio. LIGO first detection, a pair of black holes spiraling into each other, became a fleeting chirp, a sound so faint it was almost lost in the noise of the universe. Later collisions revealed deeper tones, some rumbling like thunder, others clicking like a metronome. These aren't just artistic interpretations, they're data made intimate, allowing scientists to listen for subtle variations that reveal the object's masses, spins, and distances. So while space may lack the soundtrack we're used to, its silence is an illusion, one we've learned to shatter with ingenuity. Every converted vibration is a reminder that the universe isn't quiet. It's just speaking a language we had to teach ourselves to hear. Imagine an alien civilization so advanced that they don't just listen to the universe's music, they compose with it. While we're still learning to translate cosmic vibrations into sound, a society millennia ahead of us might treat the interstellar medium as their concert hall, bending gravitational waves and electromagnetic pulses into symphonies spanning light years. The concept isn't pure fantasy. SETI researchers have long speculated that extraterrestrials could encode messages in pulsar timings or manipulate neutron star emissions like cosmic tuning forks, turning natural phenomena into the universe's most powerful communication array. Consider the possibilities of gravitational wave engineering, a civilization capable of moving black holes or creating artificial ones could position them to collide at precise intervals, generating low-frequency chirps in a pattern detectable across galaxies. These wouldn't be random cosmic events, but deliberate broadcasts like ringing a giant bell to announce, "We're here." The technology sounds like science fiction, but the physics is sound. Just as we manipulate radio waves for communication, a sufficiently advanced society might harness space-time itself as their transmission medium, with mergers as their Morse code. Then there's the artistic angle. Picture a species using magnetars as interstellar instruments, triggering controlled starquakes to produce specific X-ray frequencies. By carefully timing these eruptions, they could create melodies lasting centuries, songs so slow human ears would need time-lapse technology to perceive the rhythm. Some astronomers suggest we might have already detected such music without realizing it. The repeating fast radio bursts that baffle scientists. They could be accidental leakage from an alien civilization's attempt to modulate pulsar emissions, like cosmic musicians accidentally broadcasting their soundcheck across the universe. The most intriguing prospect is direct manipulation of the cosmic microwave background. In theory, a Kardashev Type 3 civilization, one controlling energy on a galactic scale, might imprint artificial patterns on this primordial radiation, effectively tattooing their existence onto the universe's oldest light. The resulting song would be detectable everywhere at all times, like an eternal chorus woven into the fabric of reality itself. While these ideas stretch our current understanding, they highlight an important truth. The universe doesn't just play music, it is music vibrating at every scale. And if other civilizations have learned to hear and shape these vibrations, our first contact might not come through a radio signal, but through recognizing a melody too precise to be natural, a rhythm in the cosmos that whispers, "Someone else is listening too." The future of cosmic sound research is unfolding right now, with next-generation instruments poised to revolutionize how we listen to the universe. The James Webb Space Telescope, already transforming our view of the cosmos, carries sensors so sensitive they can detect the faint infrared hum of ancient stellar nurseries, vibrations from the universe's first stars that have stretched into deep, resonant tones over billions of years. But Webb is just the opening act. The European Space Agency's LISA mission, launching in the 2030s, will deploy 3 spacecraft flying in perfect formation across millions of miles, their lasers measuring gravitational waves with such precision they could hear the merger of black holes smaller than our sun. Imagine tuning into a frequency range that captures everything from the faint whispers of colliding white dwarfs to the thunderous crashes of supermassive black holes in distant galaxies, a gravitational wave symphony finally within earshot. Closer to home, projects like the Square Kilometre Array are redefining what it means to listen to space. This sprawling network of radio antennas, spanning 2 continents, will detect electromagnetic vibrations from the earliest epochs of star formation with unprecedented clarity. Its resolution is so sharp it could pick up the radio murmur of an exoplanet's magnetic field interacting with its star, a potential clue in the search for habitable worlds. Meanwhile, pulsar timing arrays are growing more sophisticated, with observatories like Nanograv using these cosmic metronomes to hunt for the background hum of supermassive black hole binaries. The data already hints at a low-frequency chorus, a murmur of overlapping gravitational waves that could soon resolve into individual voices, each telling the story of galaxies merging in the ancient universe. But the real game changers might be the technologies we haven't yet imagined. Quantum sensors, now in early development, could one day detect space-time ripples far weaker than LIGO can perceive, perhaps even the faint echoes of cosmic strings vibrating from the universe's birth. And advances in AI are allowing researchers to sift through decades of radio telescope data for patterns human ears might miss, uncovering hidden rhythms in the noise. Some teams are already experimenting with neutrino detectors as cosmic microphones, since these ghostly particles carry information about stellar cores and supernova that even light can't escape from. What's most exciting is how these tools will work together. Picture combining Webb's infrared vision with LISA gravitational wave hearing, and the SKA's radio ears, a multisensory approach to cosmic music that reveals how electromagnetic and gravitational vibrations intertwine. We might discover that magnetars and quasars produce not just electromagnetic screams but gravitational harmonies, or that dark matter's elusive presence subtly warps the tones of passing gravitational waves like a cosmic soundboard. This isn't just about building better detectors, it's about learning to hear the universe in stereo. Every new instrument adds another layer to the symphony, helping us distinguish the soloists from the chorus. And somewhere in that growing cacophony, there might be a note we've never heard before, one that changes everything we thought we knew about the music of the spheres. You don't need a radio telescope or $1 million lab to eavesdrop on the universe's symphony, just an internet connection and curiosity. NASA and other space agencies have made terabytes of cosmic data freely available, turning your laptop into a personal stargazing station. Start with something simple like the sun's vibrations. Websites like the Solar Dynamics Observatory's database let you download raw Asteroseismology data, the sun's surface oscillations captured in precise measurements. Free audio software like Audacity can then shift these ultra-low frequencies up into the human hearing range, transforming the sun's pulsing heart into a deep, resonant hum. Suddenly, that yellow dot in the sky isn't just light. It's a living, breathing performer. For a more rhythmic experience, dive into pulsar data. The European Pulsar Network archives decades of radio observations from spinning neutron stars. Load these into programs like Sonic Visualizer, and you'll hear the metronomic clicks of cosmic lighthouses, some ticking faster than a hummingbird's wings, others slow and stately like a grandfather clock. Adjust the playback speed, and you might catch subtle variations called glitches, where a pulsar's spin suddenly changes like a record skipping. These aren't just cool sounds, they're clues about starquakes and mysterious superfluid vortices inside these dense stellar corpses. Want to compose with the cosmos? Platforms like the Chandra X-ray Observatory's sonification tools let you assign musical notes to different wavelengths of light. Take the Crab Nebula, assign X-rays to piano keys, visible light to strings, and infrared to synth pads, and suddenly you're orchestrating a supernova remnant's afterlife. The internet is full of amateur astronomers who have turned these techniques into stunning art, like the musician who mapped Saturn's radio emissions to a marimba scale, creating an eerie, percussive soundtrack for the ringed planet's auroras. The magic happens when you start layering these cosmic tracks. Combine the sun's bass line with Jupiter's magnetospheric chorus recorded by the Juno spacecraft. Add the whistle of solar wind from NASA AC satellite, and you've got a celestial jam session unfolding in real time. Online communities like the Astrosonic Collective share tips for filtering out Earth radio interference, letting you isolate the universe's purest signals. Some enthusiasts even hook up MIDI controllers to live telescope feeds, turning incoming data from observatories into improvisational space music. This isn't just play, it's citizen science. Amateurs have spotted anomalies in sonified data that algorithms missed, like the faint whoosh of a previously unknown meteor shower in archived radio recordings. Others have created audio fingerprints of exoplanet transits, training their ears to detect subtle dips in starlight that might indicate new worlds. When you listen actively, you join a tradition stretching back to Galileo, exploring the cosmos with whatever tools you have, discovering its music one note at a time. There's something undeniably primal about the way cosmic sounds resonate with us, not just as scientific curiosities, but as emotional triggers that bypass logic and speak directly to the subconscious. When researchers at the University of California played sonifications of solar wind data for test subjects, they noticed something unexpected. Even people with no astronomy background described feeling a sense of awe, as if they'd glimpsed something vast and ancient. Rain scans revealed heightened activity in the default mode network, the same region linked to introspection and self-reflection during moments like staring at a starry sky or standing at the edge of the ocean. It's as if these sounds tap into a deep-seated recognition, a reminder that we're connected to forces far grander than ourselves. This reaction isn't accidental. Evolutionary psychologists suggest that awe evolved as a survival mechanism, sharpening our attention to vast, unpredictable phenomena, think thunderstorms or mountain vistas, that might signal opportunity or danger. Cosmic sounds trigger this same response on a cosmic scale. The low, resonant hum of a black hole's gravitational waves or the eerie whistle of a magnetar's magnetic field don't just register as noise, they feel like direct lines to the sublime. Composers like Hans Zimmer have harnessed this instinctively, blending real sonifications into film scores for Interstellar and Dune to evoke otherworldly grandeur. The result isn't just cinematic, it's neurological. Studies show that exposure to these sounds can temporarily reduce stress hormones and increase feelings of connectedness, a phenomenon dubbed the overview effect in audio form. But the power of cosmic music goes deeper than fleeting emotion. Therapists at the Johns Hopkins Center for Music and Medicine have experimented with space-inspired soundscapes in clinical settings, particularly for patients grappling with existential anxiety. The slow, rhythmic pulses of neutron stars or the fractal-like harmonies of galaxy clusters seem to create a mental bridge between the personal and the universal, helping individuals reframe their worries against the backdrop of cosmic time. One patient described listening to sonified data from the Hubble Deep Field, a recording translating the light of ancient galaxies into chords, as hearing time itself, a perspective shift that eased their fear of mortality. Interestingly, not all cosmic sounds provoke the same response. High-frequency phenomena, like the metallic screech of a quasar's jet, tend to induce alertness or even unease, while deep, steady tones, such as the vibrations of the Perseus galaxy cluster's black hole, promote calm. This duality mirrors humanity's ancient relationship with natural sounds, the comfort of a heartbeat's rhythm versus the alarm of a predator's cry. Modern apps now curate these frequencies for meditation, layering the boom of solar flares over forest ambience to create sound baths that feel simultaneously grounding and expansive. Perhaps the most profound impact lies in creativity. Artists from Brian Eno to Björk have incorporated astrophysical data into their work, not just for novelty, but because these sounds seem to unlock uncharted emotional territories. When the London Symphony Orchestra performed a piece based on Cassiopeia-A shockwaves, musicians reported an unusual sense of playing the universe, as if the music existed before they touched their instruments. This blurring of discovery and creation hints at why cosmic sounds captivate us. They're not just artifacts of science, but fragments of a melody the universe has been composing for billions of years, and we're finally learning to sing along. Long before telescopes revealed the pulsations of distant stars, humanity heard music in the heavens. The ancient Greeks envisioned celestial bodies embedded in crystalline spheres, their movements producing harmonies so perfect only the gods could hear them. Pythagoras calculated the mathematical ratios behind these cosmic chords, convinced the planets sang in intervals as precise as the strings of a lyre. Meanwhile, Norse myths told of the giant Ymir, whose bones became mountains and whose skull formed the sky, a drumhead stretched taut, reverberating with the thunder of Thor's hammer. These stories weren't just fanciful tales, they were early attempts to explain the sublime order glimpsed in the night sky, a rhythm sensed even when it couldn't be heard. What's striking is how these myths foreshadowed modern discoveries. The Hindu Rigveda described vibrating strings underlying creation, a concept eerily echoed by string theory's proposal that subatomic particles are tiny, oscillating filaments. Indigenous Australian traditions speak of the songlines, pathways across the land and sky created by ancestral beings whose songs still resonate in the stars. Today, we know those songs are real. The vibrations of stars, the electromagnetic hum of nebulae, even the gravitational waves rippling from colliding black holes. The difference, now we have instruments to translate those vibrations into melodies our ancestors could only imagine. Consider the Chinese legend of the Weaver Girl and the Cowherd, two lovers separated by the Milky Way and allowed to meet just once a year. Modern astronomy reveals their Bridge of Magpies is actually the Cygnus superbubble, a vast structure where stellar winds and supernova generate ultrasonic shockwaves. When sonified, these waves produce eerie, flute-like tones, as if the myth preserved an intuition about the region's acoustic nature. Similarly, the Navajo concept of the holy wind, a vibrational force connecting all life, mirrors the interstellar medium's low-frequency oscillations, which scientists now detect as a faint, omnipresent hum. These parallels raise a profound question. Did ancient cultures, lacking our technology, perceive cosmic patterns through other means? Some researchers suggest that rituals involving rhythmic drumming or chanting might have been unconscious attempts to harmonize with universal frequencies. The Dogon people of Mali, for instance, knew of Sirius B, a white dwarf invisible to the naked eye centuries before telescopes confirmed its existence. Their ceremonial dances, timed to Sirius's 50-year orbital cycle, hint at a deep, perhaps intuitive, grasp of celestial mechanics expressed through music and movement. The real magic lies in how these myths and modern science converge. Kepler's 17th century vision of planetary music was wrong in detail. Mars doesn't literally sing a tenor D, but correct in essence. We now know planets and stars do vibrate, their frequencies revealing compositions of gas and plasma. The universe isn't a silent void, but a dynamic arena where gravity and magnetism compose a symphony older than time. And just as myths sought to connect humanity to the cosmos, today's sonifications remind us we're not just observers. When we listen to the converted radio waves of a quasar or the oscillations of a red giant, we're fulfilling an ancient impulse to hear the music of the spheres, not as metaphor but as revelation. The universe's hidden melodies have long inspired artists to bridge the gap between science and creativity. transforming raw cosmic data into breathtaking musical experiences. Take composer Terry Riley's Sun Rings, a multimedia piece commissioned by NASA that weaves together plasma wave recordings from the Voyager probes with soaring orchestral arrangements. The result is haunting, a chorus of interstellar whistles and crackles sampled directly from Jupiter's magnetosphere, layered over minimalist strings that mirror the vastness of space. Riley didn't just set astronomy to music. He revealed how celestial vibrations could evoke emotions no textbook ever could. Meanwhile, sound artist Laurie Spiegel took a more algorithmic approach with the expanding universe, her 1980 electronic composition based on Kepler's laws of planetary motion. Using early computer software, Spiegel translated orbital dynamics into pulsing synth sequences, creating a hypnotic soundscape where each tone represents a celestial body's speed and distance. The piece feels alive, its rhythms ebbing and flowing like gravity itself, a reminder that mathematics and music share the same cosmic language. Today, her work influences everything from film scores to experimental techno, proving that scientific accuracy can coexist with artistic innovation. For a truly immersive experience, Icelandic musician Jónsi collaborated with astrophysicists to create Liminal, an album incorporating sonified data from black hole mergers and solar flares. One track features the resonant boom of a gravitational wave shifted into human hearing range, its bass frequencies vibrating through listeners' bones like a primal echo from the cosmos. Another layers the radio emissions of pulsars into arrhythmic glitches, mimicking the disorienting beauty of deep space. The album's genius lies in its restraint. Jónsi lets the universe's own sounds take center stage, using subtle instrumentation to heighten their emotional impact rather than overpower them. Visual artists have also joined the cosmic chorus. Team Lab's resonating life in the acoustic space installation transforms real-time solar wind data into an ever-shifting soundscape, where visitors' movements trigger ripples of light and tone modeled after interstellar shockwaves. Walk through the exhibit and you're literally dancing with particles from the sun, their energetic collisions rendered as ethereal chimes. It's science as sensory poetry, dissolving the line between observer and participant. Perhaps most ambitiously, the European Space Agency's Music of the Spheres project invited composers from 6 continents to create works using data from Gaia, the star mapping satellite. A Mongolian throat singer wove the proper motions of nearby stars into overtone chants, while a Brazilian percussionist translated stellar metallicity into polyrhythms reminiscent of rainforest ecosystems. The collection celebrates how cultures worldwide interpret the cosmos through their unique musical lenses, proof that the universe's symphony has as many interpretations as it has listeners. These projects aren't just artistic curiosities, they're tools for connection. When a child hears Saturn's radio emissions turned into a gamelan melody or a supernova's light curve morphed into a harp glissando, astronomy stops being abstract. It becomes a story told in a language we're all born understanding, the language of rhythm, harmony, and resonance. And in that translation, we're reminded that the universe isn't just something we study. It's something we feel. What if the universe's music isn't just beautiful, it's a code? Beneath the chaos of supernova crashes and pulsar beats, scientists have detected recurring mathematical patterns in cosmic vibrations, ratios so precise they mirror the intervals of a musical scale. Take the harmonics of a star's oscillations. The frequencies at which it pulsates often align with whole number multiples, like notes in a chord. These aren't random noises, they're expressions of universal physics, governed by equations that dictate how matter vibrates under pressure, whether in a violin string or a neutron star's crust. Some researchers argue this isn't coincidence but evidence of a deeper symmetry, one that could hint at a universal language woven into the fabric of reality itself. The idea isn't as far-fetched as it sounds. Ancient philosophers like Pythagoras believed mathematics and music were two sides of the same coin, with planetary motions following harmonic ratios akin to a lyre's strings. Today, we see echoes of this in the orbital resonances of exoplanets' worlds, whose gravitational dances lock into neat fractions, like two planets circling their star in a perfect 2-to-3 rhythm. Even the cosmic microwave background, the afterglow of the Big Bang, contains peaks and troughs spaced like the overtones of a vibrating string. These patterns suggest an underlying order, a kind of cosmic sheet music where the laws of physics dictate the notes. But could this language be universal in the truest sense, understandable not just to humans, but to any intelligence? Consider how dolphins interpret sound in 3 dimensions, or how bats map their world through ultrasonic echoes. Our musical scales are based on human perception, yet the ratios behind them, like the octaves 2-to-1 frequency doubling, are mathematical truths independent of biology. A supernova's shockwave or a black hole's ring-down vibrates with these same ratios, meaning an alien civilization might hear them as structured harmonies even if their ears work nothing like ours. The late physicist Max Tegmark proposed that mathematics itself might be the universe's native tongue, with cosmic vibrations serving as its dialects. The most compelling evidence comes from sonification projects that reveal hidden patterns. When researchers translated the orbits of TRAPPIST-17 Earth-sized planets into musical tones, they discovered a near-perfect arpeggio, a sequence where each world's orbital period corresponded to a note in a descending scale. Similarly, the vibrations of our sun, when sped up, produce a hum eerily reminiscent of Tibetan singing bowls. These aren't artistic flourishes, they're direct translations of physical laws into sound, suggesting that what we call music might just be our word for vibrations obeying universal rules. Critics caution against over-interpretation. Just because celestial phenomena can be mapped to musical intervals doesn't mean the universe intends them as communication. The ratios we find beautiful might be evolutionary accidents, hardwired into our brains because they helped our ancestors recognize patterns in nature. Yet even skeptics admit the precision is striking. When LIGO detected gravitational waves from colliding black holes, the frequencies followed a trajectory that, when sonified, matched the suspenseful rise of a cinematic crescendo, not because the universe is dramatic, but because the physics of merging masses naturally produces that shape. Perhaps the truth lies in between. The universe may not be speaking to us in scales and chords, but its vibrations are undeniably structured by the same mathematics that govern sound. Whether that's enough to call it a universal language depends on how we define the term, but one thing is certain: every time we listen to the cosmos, we're not just hearing noise. We're eavesdropping on the fundamental rules that shape everything from atoms to galaxies, a song written not in notes, but in the very laws of existence. In 1977, the golden records aboard Voyager 1 and 2 carried a curated snapshot of Earth sounds, from Bach concertos to the crackling of fire into the void. It was a hopeful gesture, a musical handshake extended to any civilization that might one day intercept it. But today, as we stand on the brink of an era where we could actively broadcast our presence into the cosmos, that optimism is tempered by urgent ethical debates. The question isn't just whether we can share our music with the universe, it's whether we should. On one side are the advocates of interstellar outreach, who argue that silence is a wasted opportunity. Initiatives like METI, messaging extraterrestrial intelligence, propose actively transmitting high-powered signals containing everything from mathematical sequences to cultural artifacts. Their reasoning is rooted in curiosity and connection. If advanced civilizations exist, exchanging knowledge could accelerate our collective understanding of the cosmos. After all, they point out, humanity's history is shaped by cross-cultural exchange from the Silk Road to the Internet. Why should interstellar dialogue be any different? Some scientists even suggest encoding Earth's music in laser pulses, turning entire stars into amplifiers for our symphonies. Yet this enthusiasm is met with stark warnings. Prominent figures like Stephen Hawking cautioned that broadcasting our location could be catastrophically naive, comparing it to the moment Native Americans first glimpsed Columbus's sails on the horizon. The universe, they argue, might not be a benign choir of enlightened civilizations but a dark forest where predators lurk in silence. Even if the odds are slim, the potential consequences, hostile entities intercepting our signals or exploiting our resources, are too grave to ignore. This camp advocates for the zoo hypothesis, the idea that advanced aliens might already be aware of us but deliberately avoid contact, treating Earth as a planetary nature preserve. Our sudden transmissions could shatter that fragile equilibrium. The debate grows murkier when we consider what we're sharing. The Voyager records were a diplomatic portfolio, carefully vetted to represent humanity's best. But modern transmissions could include everything from pop songs to wartime broadcasts, an uncensored feed of our contradictions. Ethicists ask, do we have the right to broadcast a child's laughter without also sending the sounds of bombings? Who decides which aspects of Earth's chorus deserve an interstellar stage? There's no global consensus, yet the act of broadcasting binds all of humanity to its repercussions. Beyond practical risks lies a philosophical quandary, the arrogance of assumption. When we beam our music into space, we're presuming extraterrestrials perceive sound as we do. Their ears might detect gravitational waves or quantum vibrations, rendering our symphonies as meaningless as a radio played underwater. Worse, our signals could inadvertently cause harm, like ultrasonic frequencies distressing alien wildlife we can't begin to imagine. Astrobiologists remind us that even on Earth, species communicate in wildly different ways. Humpback whales sing complex ballads, while cicadas use blisteringly loud clicks. An interstellar hello might be less a handshake and more a bullhorn in a sensory landscape we don't understand. Perhaps the most compelling middle ground comes from passive listening. Projects like SETI focus on detecting alien signals rather than sending our own, treating the cosmos as a vast library where we're the quiet patrons. This approach acknowledges the value of connection while respecting the precautionary principle, learning the universe's rules before joining its conversation. After all, the first step in any dialogue isn't speaking, it's learning how to listen. As our technology advances, so does the urgency of these questions. Private initiatives could soon unilaterally broadcast messages, bypassing international debate, and with telescopes like JWST identifying potentially habitable exoplanets, the targets for such transmissions grow ever clearer. The stakes are cosmic. Our choices today might echo across millennia, determining whether Earth's music becomes a bridge or a beacon for peril. In the end, the silence of space isn't just an absence of sound, it's a canvas awaiting our decisions, one note at a time. Want to conduct your own cosmic symphony from your smartphone? NASA's official space sounds app transforms raw astronomical data into interactive soundscapes, letting you swipe through frequencies like a DJ mixing tracks from across the galaxy. Pinch to zoom into the Crab Nebula's crackling radio waves, then tilt your device to modulate the eerie chorus of Jupiter's magnetosphere. Each gesture reveals new layers of the universe's hidden soundtrack. For a deeper dive, Sono Uno offers a tactile experience. Upload light curve data from any star observed by the Kepler telescope, and the app instantly generates its unique vibrational profile. Adjust parameters like tempo and pitch to hear how a red giant's pulse differs from a white dwarf's metallic ping, or overlay multiple stars to create celestial harmonies no human composer could imagine. If you prefer guided exploration, the BBC's Universe Symphony web tool is like having a virtual astronomer at your fingertips. Click on 3D-rendered galaxies to trigger their sonified emissions. The Whirlpool galaxy's spirals emit harp-like glissandos, while colliding antennae galaxies explode into percussive bursts. The interface even lets you simulate gravitational wave events, sliders controlling black hole masses to hear how a 30 solar mass merger's deep thud compares to a 100 solar mass collision's seismic boom. Educators love Chromaticos, a classroom-friendly platform where students can remix solar wind data into electronic music, isolating the sun's 5-minute oscillation cycles and layering them with synthesized beats to reveal the hidden rhythms in seemingly random noise. For those craving real-time cosmic jams, Pulsar Explorer taps into live feeds from radio telescopes worldwide. Tune into the Vela Pulsar's staccato clicks 1 minute, then switch to the slower, heartbeat-like thumps of PSR B03 tune 9+54 the next, each pulsar's rhythm visualized as a pulsing orb whose color shifts with its electromagnetic spectrum. Augmented reality modes project these celestial metronomes into your living room, their beats syncing to your footsteps as you walk circles around a neutron star's virtual wreckage. Hardcore enthusiasts flock to Astrocode, an open-source software that processes raw FITS files from professional observatories. Here, you can isolate the microwave whisper of the cosmic background radiation or amplify the gamma-ray screech of a distant blazar, then export the audio to digital audio workstations for further manipulation, turning quasar emissions into bass drops or supernova remnants into ambient pads. The true game-changer, collaborative platforms like CosmoSync, where users worldwide contribute processed audio clips to a growing library of stellar samples. A musician in Reykjavik might upload the Doppler-shifted harmonies of the Andromeda galaxy's approaching stars, while a student in Mumbai tags the infrasound rumble of an Antarctic neutrino detector picking up cosmic rays. Together, these fragments form a living archive of the universe's acoustics, not just for listening, but for creating. When a London producer recently crafted an entire album using only CosmoSync samples, the resulting tracks carried something profound, proof that humanity's creativity and the cosmos' natural music aren't separate, but part of the same endless composition. The universe's symphony isn't just a metaphor, it's a living, breathing reality, a cosmic performance where every star, planet, and black hole plays its part in an endless composition. These melodies, whether the deep hum of gravitational waves or the piercing whistle of solar winds, reveal a universe far more dynamic and interconnected than we ever imagined. They're not just echoes of distant events, they're threads tying us to the cosmos, reminders that the atoms in our bodies were forged in the same stellar furnaces that now sing across the void. What makes this cosmic music so profound isn't just its scale, but its intimacy. When scientists translate the vibrations of a star into audible tones, we're not just hearing data, we're eavesdropping on a conversation billions of years old, one that began long before Earth existed and will continue long after we're gone. The rhythmic pulses of a pulsar, the resonant boom of colliding black holes, even the faint hiss of the cosmic microwave background, these aren't just scientific curiosities. They're the universe's way of telling its story, a narrative written in frequencies we've only just learned to hear, and this is just the first movement. With every technological leap from gravitational wave detectors to AI-powered radio telescopes, we're tuning into harmonies we once thought were silence. Future missions like LISA will capture the low-frequency murmurs of supermassive black holes, while quantum sensors might one day detect the faintest vibrations of dark matter. Each discovery adds new instruments to the orchestra, revealing layers of complexity we never knew existed. But the true magic lies in how this symphony changes us. Hearing the cosmos transforms it from an abstract expanse into something visceral, something alive. It's one thing to read about a supernova. It's another to listen to its shockwaves ripple through interstellar gas, a sound both beautiful and terrifying. These vibrations bridge the gap between knowledge and wonder, between science and art. They remind us that the universe isn't just something we observe, it's something we're part of, a grand composition where we're both audience and participant. So as you look up at the night sky, remember, you're not staring into silence. You're surrounded by music, a celestial soundtrack playing on a loop for billions of years. The instruments may be strange, the scales unfamiliar, but the melody is unmistakable, a song of creation, destruction, and endless reinvention. And with every passing moment, we're learning to hear it a little more clearly, one note at a time. If this journey through the universe's hidden melodies left you in awe, you're not alone. Every time we listen, the cosmos surprises us with new rhythms, new voices, and new mysteries waiting to be unraveled. But here's the thing, this symphony never stops playing, and neither does our exploration of it. By hitting that subscribe button and tapping the notification bell, you're not just keeping up with our videos, you're joining a community of cosmic listeners, all tuning in to discover what the universe will reveal next. Whether it's the haunting hum of a black hole or the rhythmic ticks of a pulsar, there's always another note waiting to be heard. Now, we want to hear your voice in this celestial chorus. Drop a comment below and tell us which cosmic sound left you spellbound. Was it the solar wind's ghostly whistle, the deep boom of colliding galaxies, or something else entirely? Your thoughts spark conversations that make these discoveries even richer, and who knows, your question might just inspire our next deep dive into the mysteries of space. And if you know someone who'd love this cosmic soundtrack, share the video. Tag the friend who geeks out over black holes, the family member who always points out constellations, or that coworker who needs a reminder that the universe is way cooler than spreadsheets. Together, we can turn more ears toward the wonders above, because the best discoveries are the ones we make and share as a community. Finally, a huge thank you for lending us your time and curiosity. Whether you're a lifelong space enthusiast or just dipping your toes into the cosmic unknown, your presence here is what makes this journey meaningful. The universe may be vast, but it's connections like these between stars, stories, and the people who love them that make it feel like home. Now, go outside, look up, and listen. The symphony's always playing. You just have to know how to hear